Hello, welcome back to Engineering 211 Statics. We were working on 2D trusses last time, and I want to finish up that work with a couple of quick problems and then venture briefly into three-dimensional trusses. We're not going to spend a lot of time on that because conceptually it's very much the same. And that will really wrap up our truss work, and then we'll move on to what happens when things are not comprised solely of two force members, in that if they have multiple force members. So to get started with that, I'd like to look at this problem here, where we have a truss. We've got a looks like a variety of loads on it. Each one of these panels is 4 meters, so it's metric. It's 4 meters in length, and the whole thing is 6 meters high. From there to there is 6 meters high. We've got a variety of loads, 10 kilonewtons, 10 kilonewtons, and 10 kilonewtons, all of those straight down. The loading is not symmetrical, so we probably would not expect the forces in the members to be symmetrical. That is, the force in this member FG may not be the same as AB over there. Well, what we're looking for is the force in DJ. So we're interested in the force in that member right there. And we've talked about method of sections. Probably rather than starting here at A and working our way over to here at D with a method of joints, we'll try method of sections. Now you might say, well, could we start with D and get it directly? Well, there would be 1, 2, 3 unknowns in that equation, so that wouldn't work, and we'll come back and look at that in a moment. But if I do method of sections, I might be tempted to take a section down through here like that, or I could do the mirror image on this side. The only problem with that is I go through 1, 2, 3, 4 members, so I'm going to end up with a section with 4 unknowns, and I can only tolerate 3 unknowns. That would be the same thing that if exactly the same situation if I were to come through here, slice through there, again 1, 2, 3, 4 unknowns. Now some people might be saying, well, why don't we do a section like this? If we slice through here and have a section, let's get exactly what we would have if we did a method of joints up there. So I could say that I have CD here, and then I would have DE here, and then I would have DJ, like that, and I end up with 1, 2, 3 unknowns. So that's kind of an interesting section in that all of those forces for that particular section are coincident on a point. So I actually don't get 3 equations. I don't have a moment equation. My sum of my moments would be an equation 0 is equal to 0. It'd be a trivial equation. So I can only in that case tolerate 2 unknowns. So essentially it goes back to a method of joints problem. So how am I to solve this? Well, the way that we will solve it is to essentially, for instance, take a section through here. And I'll make this with a heavy line. I'm going to do a section through there. And of course, with that, I'm not going to find what I'm looking for, but I will find this CD. And once I then find that CD, I can come over to D here, say at D. I can come over to D here and come up with this. So once I've gone through a method of sections here, I will find what D is. Then or excuse me, not D, but come up with what CD is, come up with this one, and be able to do that. So that's the scheme. The first thing I need to do is I'm going to need to find the reactions here. You could imagine that you would have a reaction there and a couple of reactions here. So I think I'll go through a quick Freebody diagram of this thing and get the reactions. I think I'm going to look at the left-hand side, so I really only need to find that reaction at A. So let's do that. Lay this thing out here like this. We would have this one G. I would have A in the Y direction, A in the X direction, and then I've got the loads here like this. Okay, and if we were to look at distances, what distances do I have? I have 4 meters there, 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 and 4 meters there, right? For a total 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Yes. Okay, and this was 10 kilonewtons, 10 kilonewtons, 10 kilonewtons. So if I then, going through this, if I sum the moments, let's say about the point G, setting that equal to 0, what am I going to come up with? I'm going to have 10 times 8, that's that one, plus, it looks like some of the moments about that point looks like I'm taking that way as positive, right? Plus 10 times, what's this distance? 1, 2, 3, 4, be 16. So that's that one. Plus 10 times 1, 2, 3, 4, 5, be 20. So that's that one. And then I have to subtract off A times the total distance, 1, 2, 3, 4, 5, 6, 24, right? So I could say then, I should say that's AY. So AY is equal to what? 80 plus 160 plus 200 divided by 24, which turns out to be, I think, 18.3 kilonewtons. Let me double check that. Let's clear it up here. There we go. Yeah, 18.333. So 18.3 kilonewtons. If I did sum the forces in the horizontal direction, setting that equal to 0, I would have AX, no other horizontal, so AX is equal to 0, as you probably expected a while ago. So we've got this now, so I can go ahead and look at that section. Let me do that. And we'll say that this is page 2. I'll keep this picture here just for reference. So this section is going to look like, I'm essentially drawing this piece right here. Right there. Not a great section, but and we've got at A, we just found this was 18.3 kilonewtons. And we have 10 kilonewtons, 10 kilonewtons. And then I'm going to say that I have, and maybe I'll purposely kind of mess things up here. I'm going to say that CD is like this. I'm going to say CD is like that. I'll draw that in tension, probably not in tension on the top chord, but we'll see how that works out. And then I've got CJ here, like that. And then JK. Like that. Okay. So there's a few angles that I probably need to find in there. I probably need to find this angle here. I'll call that theta, because that would be the same as that angle there, theta. And then I should probably find this angle here, beta. I don't. Maybe I'll need that. Maybe I won't. If we look at that one, if we come over here, if this is 6 meters, and this, if this is 4, and this is 4, and this is 4, and this is 6, then by ratio and proportion or similar triangles, this would be 4 here, and this would be 2, wouldn't it? Okay. So now if I have something for instance, this angle in here, or this angle in here, which is what we're looking at. I look at a triangle with this one. If this side is 4 and that side's 4, we know that has to be 45, doesn't it? Now theta is not quite as obvious. I could say that theta, put that over here, theta is going to be equal to the arc tangent of what's our opposite side. Well, I could look at this, a whole side of this thing. I mean, you could come over here and look at this little triangle with 2 and 4. You could look at this, you'll get the same answer. The opposite side would be 6, and the adjacent side is what? 1, 2, 3. 3 times 4 is 12. So what's that turn out to be? 26.6. Okay, so I've got theta 26.6 degrees. So that sets me up. Remember, what I'm really wanting out of this thing is I want CD. So I can do this. I'll do it a couple different ways. I think this is going to be hopefully kind of interesting. The first thing I think I'm going to do is I'm going to sum, if we look at this, that's point J, right? So I'm going to sum the moments about J. Sum the moments about J, setting that equal to 0. Why don't I go ahead and take clockwise positive. And what I'm going to have the horizontal piece of this, so that's going to be equal to CD times the cosine of theta. I'll just write theta. We know it's 26.6 times the distance of 4, because this distance here, that's 4, isn't it? This was 2. That's 4. That one's 6. So CD times the cosine of theta times 4. And then what am I going to have? Plus, I've got to deal with the vertical part of CD, don't I? This horizontal piece is right there. The vertical piece is right there. So I have plus CD times the sine of theta times the distance that acts through, which is this distance here, right? Which is going to be 4. And then I'm going to have to add to that, let's see, 18.3 times the distance of 12. Isn't that right? From J to A. Yep, that's 12. And then I have to take into account the loads, minus 10 times the distance of 4 for this one, minus 10 times the distance of 8 for that one. So this one is a distance of 8 because this is 4 here. So when I go through solving for CD, what does CD turn out to be equal to? Well, let's see, I can move these to the other side, so I get minus 18.3 times 12 plus 10 times 4 plus 10 times 8 divided by, those both have 4's in them, so I have 4 times the cosine of 26.6 plus the sine of 26.6, that being theta. So this turns out to be equal to, when I ran the numbers, we got minus 18.6 kilonewtons. Let me double check that. Yeah, minus 18.55, we'll say minus 18.6 kilonewtons. And I suspected that I'd put this in the wrong direction. Again, oftentimes we have compression on the top chord. We drew it in tension, so this is, that negative indicates negative tension, doesn't it? Which we could say then that CD would be equal to 18.6 kilonewtons in compression. Now we're not necessarily looking for CD, but CD is going to get us to what we ultimately want. Before I head off onto that, let me look at, I could say OR. And one of the things we could do is we could look at this CD, make a little diagram here. instead of breaking this up into two pieces, sometimes you'll see people only break it up into one piece, and that would be looking at what's going right here with that CD. You could imagine that if we had a line that was across here, there's a line, there is B, that point right there. Here is C, that point right there. And here is D. And that force CD would be on that, wouldn't it? Okay. So I'm going to say that there is the force CD. And instead of breaking it up at this point here, this point C, instead of resolving it at C like we did, we resolved it there, and we resolved it there. I'm going to resolve it at this point D. So I'm going to say that I have two components here, like this at D, where again this is CD times the cosine of theta, and likewise this would be CD, because these are points here. That's point B, that's point C, this is point D. Likewise, this would be CD times the sine of theta. I'm not going to have to use that though, because now that I've broke that up, if I broke it up at D, I've got the vertical piece going like that and the horizontal piece going like that, and when I sum the moment about J, what do I get? Again, take clockwise as positive. I get CD times the cosine of theta, and I've broken it up here, so what distance is it acting through? It's now acting through 6, isn't it? Do I have to worry about this CD sine theta? No, because that actually intersects that, doesn't it? Okay, so we could put 0 in there. Then I'm still going to have the plus 18.3 times 12 minus 10 times 4 minus 10 times 8. The rest of those are exactly the same. Okay, so when I go through solving this, I can say that CD is equal to minus 18.3 times 12 plus 10 times 4 is 40 plus 80 divided by what? 6 times the cosine of 26.6 degrees. And that should turn out to be minus 18.6 kilonewtons. Let me double check that. Yeah, minus 18.56. Really the same thing that we got up there, slightly different out at the hundredths place due to probably round off. This answer is probably a little more off because I'd use both sine and cosine up there. But anyway, if you see someone doing something like this and you go, whoa, there's two components, well, this is what they're doing. They broke it up at point D. And we saw this when we were taking a moment. You could really look at any point on the line, taking the moment about any point on the line of action of that. I think we had that problem, that example problem, where you had a person pulling on a rope, and we took a distance, our R vector, from one point on the rope and also another point on the rope, and got the same answer. Same thing that we're doing here. We took a R vector going from essentially there to there with this one, and in this case we took an R vector going from there to from J up to where D was. So if you see someone do something like this and you wonder how does that work, that's what's going on. Well, the important thing that we walk away from this is that CD is 18.6 in compression. So let's go back to this picture right here. I'm going to need to recognize that this is theta, isn't it? Okay, and likewise, that's going to be the same angle. So let's see if we can do that. So I get caught up with my notes there. So we've got then we're going to do a free body diagram at D, and that's going to look like this. There's no load at D, so all I have is this CD, and I've drawn this CD in compression. I could draw it in tension and put a negative sign if I wanted to, but I'm going to draw it in compression and put the positive 18.6, and then I will draw DE. So I'll have DE like that. This angle is going to be theta. This angle is going to be theta. And then we have, and I'll just put this here, DJ. I think we recognize if those are both going up, DJ is probably going to have to be going down. And so that is point D. We don't have any external loads. If I sum the forces in the horizontal, setting that equal to 0, what do I have? I've got 18.6 times the cosine of theta minus DE times the cosine of theta is equal to 0. When I solve that, I find that 18.6 cosine theta is equal to DE cosine theta, so DE is equal to essentially what we had CD, which was this, equal to 18.6 in compression. Now again, that's not necessarily what we're looking for. What we're looking for is this DJ. So if I sum the forces in the vertical direction, setting that equal to 0, I will have 18.6 times the sine of theta for this one. Then I got the same thing for that one, so why don't I multiply that by 2, because there's 1 here and 1 there, and then subtract dj. So I can say that dj is equal to 2 times 18.6 times the sine of 20, what do we have, 20, theta was 26.6, 26.6 degrees. Okay, so when we run through that, we get a positive 16.6 kilonewtons. Let me double check that. Yeah, 16.6, 16.7. I'll stick with 16.6 kilonewtons. So we could say that dj was equal to 16.6 kilonewtons. We got a positive number. We drew it in tension, so it is in tension. Okay, so that'd be our answer for DJ. When we were looking for this one right here, we now know that that is 16.6 kilonewtons in tension. And the reason that I went through this problem is to show you that sometimes we can't be quite as direct as we may want to. I couldn't figure out a way to take a section and get this directly, so I took a section over here, came up with this character, and then used that character right there to do a quick method of joins. You can actually get to this pretty quickly. Remember, this was not necessary. I just wanted to talk about that and show you how you could do this with an alternate method if you ever see someone doing that. So the last two-dimensional problem that I want to look at is I'd like to just spend a little bit of time talking about zero force members. That usually seems to hang students up quite a bit, trying to sort out what's zero force and what's not zero force. So let's go through this one. And what we'd like to do is just find the zero force members in here. That's our task. So if I were to do a quick free body diagram around this point here, we would end up with something that looks like this. Probably CD would be in compression. Probably DE would be in compression. And whether we put them in tension or compression is not important. The negative sign would take care of that. But if I come in here with this force like this, DF, we know that has to be 0 because I have no other load. If I were to sum the forces in a direction that's perpendicular to this direction, that has to be equal to 0, doesn't it? So that's a 0 force member. So that's 0 force. Then, with that being 0 force, if I were to come down and do a free body diagram at F, so I'd probably end up with GF there and EF, like that. Probably in tension, but again, if I have drawn them the wrong way, that's not going to change my conclusion here. And then I have CF. And again, if I sum the forces in a axis that is perpendicular to this one, I recognize that that CF has to be equal to 0, doesn't it? So that's 0. Well, the nice thing then about this is recognizing whatever I have in this one here has got to be equal to that. So CD would be equal to DE. And also with this, that GF would have to be equal to EF. That this one would have to be the same as that one. Well, we can start to do this pretty quick. Down here, if we look at G, while we have a load up here, what do we have going down here? At G, we would have GF and GH, and then we've got this CG. Again, recognize that has to be 0, doesn't it? Okay, so then HG has to be GF. This would be the same as that, and that, and that, wouldn't it? Now, we don't want to get too hasty with this, because if we come and we look at a free body diagram over at B, so I have something like A, B there, and then BC here, and BH there, and 2 kilonewtons. This force in the member BH is definitely not going to be equal to 0. Now, if these happen to be at a right angle, maybe we'll just say for sake of argument those are at a right angle. They don't necessarily have to be. Let's say that we define those, that those are. We know that this this value here is going to be 2 kilonewtons, isn't it? Okay. So then if we come down and we look at what's going on at H, I'm going to have AH, I'm going to have H or GH, and then I had this probably in compression, this value BH, and finally something like this. I bet this CH is going like that. Well, this we said is non-zero, so if that's non-zero, then this would be non-zero, right? Okay. So it looks like the extent of our 0 force members is on CG, is on DF, and is also on CF. So being able to recognize those can be an advantage in making the problem. This problem is going to solve a lot quicker than we might have thought of before we recognize those 0 force members. Well, that's the last plain two-dimensional problem that I'm going to look at. What I'd like to do now is to look at a three-dimensional problem. And with a three-dimensional problem, you almost always use a method of joints. Okay. Method of sections, theoretically, you could use method of sections. There'd be nothing wrong with that, but you end up, you end up with some odd plane. I mean, you could imagine putting a plane through there and trying to figure that out. That gets pretty tough to try and keep sorted out. So method of joints, while it is fairly tedious, it is more more methodical, you just go from point to point to point. So we usually use method of joints. Theoretically, you could use method of sections, but it's going to be kind of hard to keep track of. But with method of joints, then we have the equations: the sum of the forces in the x direction is equal to 0, sum of the forces in the y direction is equal to 0 at each joint, and sum of the forces in the z direction is equal to 0 at each joint, right? So when we do a joint, a pin connection, or in 3-dimension you think of it more as a ball and socket connection, then you're going to have 3 equations, and you can tolerate 3 unknowns at a particular point. Well, let's try this problem here. Let's say that we add 1,000 pounds to this. We have some sort of kind of a jack stand or a support made out of these thin members. Members AB and AC and AD come down to then an equilateral triangle that's 10 inches on a side. The vertical distance on this thing is 16 inches. And we'd like to find the force in AB. We'd like to find the force in this one. We'd like to find the force in AC. That is the force in that one. And of course then AD. So we'd like to find the force in those 3 members. Well, we'll get started with this by working out some geometry. If I look at an equilateral triangle, that's not much of an equilateral triangle, but I try and find the center of this, essentially where this projects down from point A. I could do this by putting some perpendiculars in here. So that point there and that point there are the same. And let's see, if it's an equilateral triangle, what am I going to know about this? Well, I'm not doing this triangle any services. There we go. So I could say that this would be what? 60, because that's part of an equilateral triangle. If that whole thing is 60 and this is bisected, then that's going to be 30, isn't it? And then I know that this is 5 and this is 5 inches. And we had total distance there 10 inches. So if I want to try and find a couple of distances here, let's say that I want to know this distance here. And maybe I want to know that distance there. Okay. So this distance here is really just going to be what? 10 inches times the sine of 60 degrees. That's just really finding this side here, isn't it? Okay, which turns out to be 8.66 inches. Okay, and then this distance here is going to be what? Let's see, 5 inches divided by the cosine of 30, because I could say that this is 5 inches. This would be 30 degrees. So I'm really looking for the hypotenuse. I know the side that is adjacent to that 30 degrees, so I could say that this is 5 inches divided by the cosine of 30 degrees, which turns out to be 5.77 inches. Let me double check those. Yes. So now I could then say that this would be the difference between those. That would be 8.66 minus 5.77, which gives me 2.88, right? 2.88 inches. Okay, so we've got that. So what I'm going to do with this thing is I'm going to do a Freebody diagram at the joint A. And what's that going to look like? Well, I've got this 1,000 pounds acting down. And then I've got 3 forces coming up into here, don't I? And so I'm going to say that this is force AB. And maybe I will change things. In the past, I've always tried to do them in alphabetical order, but here maybe maintaining a directional sense is a little better. So maybe I'll name this BA. So that's from B to A. So I'm going to break with my convention of doing an alphabetical order and change to trying to indicate which direction it goes. So I'm going to say that this is from C to A. So we'll say CA. And I'm going to say that this is from D to A. So I will say DA. Okay, so that's what I've got going there. I'm not going to try and put a lot of geometry in there because I'm going to refer back to this figure for the geometry. The other thing that you'll notice is I just put these all in compression. Okay, I think probably if we sit back and look at this, we'll probably realize that we're going to be right. A lot of times, again, in 3 dimensions, it's kind of hard to figure that out from the get-go. So some people just out of habit always put all the forces coming out of the pin or the joint or all the forces going in, let the negative signs take care of those pieces. So again, you don't have to worry too much about that. Put them in, and the negative signs will tell you that. Obviously, if you know beforehand, it's nice to try and avoid negative signs, but it's nothing to spend 20 minutes on an exam trying to figure out which direction that goes. So with that Freebody diagram, I think I can start to work this out. I'm going to go through these equations, maybe not directly at first, but we'll get there. So let me look at a bottom view of this to get a little better sense of direction. I'm going to say, I'm going to put that the x-axis comes right out through C. So I'm going to say that that's the x-axis. And I'm going to say that the y-axis is then this way. And then I'm going to say that the z-axis that's the z-axis where this 1,000 pounds was. Okay, so with that, if I look at this bottom triangle, I think this will be worth going through. So there's the center point there, and I have this y-axis here, and I have the x-axis here. So this would be C, and this is B, and this is what, D? And I'm left then with let's see, some geometry here. I can say that this is 5 inches, isn't it? Likewise, I mean, this would be 5 inches. This dimension here was that dimension that we figured out here. That was that 2.88, wasn't it? So 2.88 inches. And then this dimension here is this 5.77, because this was the center point there. 5.77 inches. And probably all total on this problem, the most important, well, a very important part, I'm not going to say the most important part, but a very important part, and certainly the most difficult part, I think, is probably geometry. We've spent more time trying to sort out the geometry than anything else. Well, let's see if we can finish this then. So I'm going to say that the sum of the forces, let me do this over here, sum of the forces is equal to 0. So I'm going to write a vector equation for all of these, and we'll say, remember that a force in vector form is equal to its magnitude times a position vector for that force divided by the magnitude of that position vector. So we're going to see that in this one. So what do we have here? I have that 0 is equal to, I've got 3 forces. This is my Freebody diagram. I've got the BA, the CA, and the DA, and then I've got that 1,000 pounds. So let me put that 1,000 in. That's a minus 1,000 in the K direction, because that was going straight down there, wasn't it? Okay, in the minus Z direction. So minus 1,000 in the K direction. And then I'm going to have DA. So I'll say that I have DA here, the magnitude DA, and I'm going to have to multiply that by a position vector. How do you get from D, this point here, or that point there, to A? Okay, well, imagine how you would get from D to this center, and then it's pretty easy to get to A. You just have to go 16 inches in the Z direction. So you're going to have something like 2.88 in the X. That gets us to there, doesn't it? So 2.88 in the I. And then what? Minus 5, because if we're right there, we've got to go minus 5 in the J. That puts us right there now, and then I'll have to go plus, like I said, 16 in the K. So if we look at this, we look at the square root of 2.88 squared plus 5 squared plus 16 squared, and I've been a little careless with my negative sign because it goes away when I square it. What's that turn out to be? Now let's see. I believe it's 17, but let me double check that. Yeah, 17. So we could say then that we are dividing this by 17. Okay, so that's DA. So on the old Freebody diagram here, I've taken care of this one. I've taken care of that one. Let's do BA and CA. So I will add to this the BA. So I'm going to say that I have BA times, imagine yourself at B. How do you get there? Well, it's going to be 2.88 in the I direction. Minus, let's see, we've got, so that gets me to a point right there. Then I'm going to have to go plus 5 in the J direction. That gets me to here. Then plus 16 in the K direction. Is that right? Let me double check that. 5, 16. Same values here. Certainly when you square that, this minus 5 and plus 5 don't make any difference at all. So again, we'd have 17. So we've got 17 here. Now if I finish up with, we've got, we did BA. So we've got CA left to do. So CA times, imagine yourself at C. What are you going to have to do? You're not going to have to go any in the X. So 0 in the I. No, I didn't do that right. Not going to have to go any in the Y. You're going to have to go, what, minus 5.77. Okay, get back on track here. So, again, starting at this point, now I have to go minus 5.77 in the X, minus 5.77 in the I. That puts me here, so 0 in the J, and then, again, 16. Because I'm sitting down here now, plus 16 in the K. Okay. So is that right? Minus 5.77, 0, and then up 16. Yes. And you could go through this, minus 5.77 squared plus 16 squared, take the square root of that. You should come up with 17 from the geometry here. We know the length of this would be the same as the length of that would be the same as the length of that, so it should not surprise us that that's also 17 if you go through that. So there's our equation. And while we might say, well, we have one equation with 3 unknowns, DA, BA, and CA, we actually have 3 equations because we could look at the I components, the J components, and the K components. So for I, what do we have? Well, let's see, no, I've got 0 is equal to, what do I have? DA times 2.88 over 17 plus BA times 2.88 over 17 plus that's actually a minus, isn't it? I'll bring that minus out. We'll leave that as a negative. Negative CA times 5.77 over 17. That's what I have for the I's. For the J's, what do I have? Well, 0 is equal to, no J there, I have dA times minus dA times 5 over 17. What do I have for J here? Plus BA times 5 over 17. Do I have any J's here? Nope, no J's there. And then K. What do we have here? 0 is equal to minus 1,000. That's a K. Plus dA times 16 over 17 plus BA times 16 over 17 plus CA times 16 over 17, right? So you could go ahead. You have now 3 equations and 3 unknowns. Three equations and 3 unknowns. And you could go ahead and maybe unknowns. That's not a very good abbreviation, is that? Let's say 3 equations, 3 unknowns. I'm running out of space, so I'll put 3 question marks. 3 unknowns. 3 question marks, 3 unknowns. So we could then solve this for dA, for BA, and for CA. I mean, it looks like this one right here is really just begging to be solved already. We move that to the other side, multiply by 17, divide by 5, and what do we conclude? That dA is equal to BA, right? And that probably doesn't surprise anyone, because we'd probably expect the magnitudes of all 3 of these to be equal to each other, wouldn't we, before we were all done by the symmetry of the problem. Well, when you go through this thing, you're going to find, I think I probably have enough room to do it here. So when you go through the matrix, and I'm not going to go through those pieces, you can go through and test it out. But when you get all done with this, you're going to conclude that dA is equal to BA is equal to CA. And you might say, well, that's nothing new. I knew that at the beginning of the problem because the symmetry of the loading, that was all the same. But this is what we didn't know. We didn't know we knew they were probably equal. We didn't know what it was equal to, and it would end up as 355 pounds. Okay. So each one of those is the same, and it's 355 pounds. Now, if they were all underneath this load and they were all supporting in a vertical sense and all supporting the same, we would think of those as 333 pounds, 1,000 divided by 3, right? Because these are splayed out a bit at a mechanical disadvantage, we would expect that number to be greater than 333, which 355 is. So I think we're in pretty good shape with that number. Now, if we wanted to fully analyze this problem, we've just done the force. We've just done the force in this one. We've done the force in that one, and the force in that one. We'd have to come down here and do a free body diagram maybe at B, and we'd look at what would that look like? Well, we'd have this compressive BA that we found. Yep, we've got BA, and then we'd have what? BD and this BC. So we'd know this, and then we could come back and solve for those others. So we're not going to get into that, but I wanted to show you how you go about one of these. And it's not particularly difficult. They can be very long. They can be a bit tedious. They can be fraught with places to make mistakes, but there's no big concepts, no new concepts here. So with that, I'll leave you with that answer. We've pretty well finished up two-dimensional trusses, three-dimensional trusses. I think you have one homework problem on three-dimensional trusses as you start to prepare for upcoming examinations and finals in the future and whatnot. I would concentrate my efforts predominantly on two-dimensional trusses. It's usually hard to come up with a three-dimensional truss problem that can be done in the time setting of a quick exam. So I think it's an important skill. Civil engineers are going to go on and spend more time with it in the future, but for now I'm going to concentrate mainly on two-dimensional trusses. When we get together next time, we'll come back and look at what happens when we start to have things that are not made up of solely two-force members. Even these three-dimensional trusses were made up of just two-force members. So when we have things that are made up of non-two-force members, we're going to call those frames or machines, and we're going to talk about how to analyze those in the future. So take care till then, and thank you for watching.